So today I will talk about how we can use Ping-Robinson equation of state to find out the compressibility of pure gas, and also you can use it for uh, multi-components. So let's open up MATLAB. I will share with these files with you later on. Okay. So in this particular case, the first file that I'm sharing, which is the name of the file is Ping-Robinson. You can find this file in the folder which I share with you later on. So in this file, what you can do, you can open up the file. I will explain to you. Before I explain this file, I want to just go to the theory part, and I want to explain a little bit about theory, what is happening. So let me open up browser and write down here. Okay, so I just want to show you the theory behind what I'm going to do. Yeah, like here. So what is happening basically? So Ping-Robinson equation of state. Let me talk about the Ping-Robinson equation of state a little bit, and then we will move to the MATLAB. So the Ping-Robinson equation of state has become popular equation of state for natural gas systems. So it is mostly used for natural gas systems, which is used in the petroleum industry. During the decade of 1970s, the scientist's name is called D. Peng, was a PhD student of Professor D.B. Robinson. So this is the teacher and this is the student, Ping. That's why it's called Ping-Robinson. So these two people, they are working in the University of Alberta in Canada. What happened? The Canadian Energy Board sponsored the project. There's a project that is sponsored by a Canadian Energy Board, and they are sponsoring and they are paying money, and they are asking them to develop equation of state specifically focusing on natural gas system. Okay, so when you compare the performance of Ping-Robinson equation of state and SRK equation of state, they are pretty close to a tie. So there's another equation of state which is called Sauve-Redlich-Cohang equation of state. Okay, this is another one. And when they are comparing Ping-Robinson and SRK results, they are pretty much close, neck to neck. But Ping-Robinson equation of state is slightly better than SRK, especially at the critical point. Critical point is the point where the gases, both the gas and the liquid, the gas phase and the liquid phase are merged together, and it is very difficult to predict what is the phase, what is the physical state of the phase at that particular point. Okay, that is the critical point. However, critical point is difficult to predict, but Ping-Robinson equation of state is predicting the critical point pretty well as compared to the SRK equation of state. That is why it is more better than SRK. A slight better performance and around the critical conditions make the Ping-Robinson equation of state slightly better for a system which contain gases and condensates. Okay. The physical form of the equation of state, normally you know Ping-Robinson equation, even the ideal gas equation is written as PV is equal to nRT. Okay, but why ideal gas equation of state is not good for real systems? Why it is bad? The problem with ideal gas solution and the real gas solution, because in the ideal gas equation, they are not good for high pressure systems. Similarly, in ideal gas equation of state, they are ignoring that there is a molecular volume between the gases, and also they are ignoring that there is an interaction between the molecules. Whereas in Ping-Robinson equation of state, which is the modifying form of van der Waals equation of state, they are introducing us important parameter which is known as A. So they include this term. This term is basically used to say that no, there is an interaction between the molecules, and that interaction between the molecules is represented by this formula. Okay. Similarly, the Ping-Robinson equation of state, they are also including that there is a molecular interaction between the molecule and there is a molecular volume, and they represent the molecular volume by the letter B. Okay. So they are basically improving the ideal gas equation by including two terms. This is the first term, which is representing the interaction between the molecules, and also they are including this term, which is representing the molecular volume. You can also rearrange this equation, and you can write the equation like this form. Okay. Now the question is, what is this alpha? What is this beta? How we can define these alpha, beta, and other parameters. So these scientists are working on the different gases, different components of pure gases, and they found out that every gas have different critical temperature, critical pressure, and they have a different accelerating factor. So based on those different information, we can give a equation, and because of different information that is related to the critical properties, we can say that this component is different for different gases. So in that context, the result will be a little bit different because every gas have different critical properties. So P-Robinson equation of state conserve that the temperature dependency of the attractive term and the eccentric factor, as I told you before. However, they represented different fitting parameter to describe the dependency of this equation, and further manipulated that the dominated denominator of the pressure correction, which is this one, sorry, numerator and denominator. Attractive term, as we can see here, the coefficient a and b are made function of critical properties of imposing critical conditions. Now they're including these two terms, which is a and b. Now they need to find out an equation for those components. First, the alpha parameter that is used in the equation is represented by this equation, which is basically proportional to the eccentric factor, and you know that every gas has a different eccentric factor, and they are also proportional to the reduced temperature, which can be calculated from the critical temperature and the temperature. So the a parameter that is used here is represented by this formula, which is basically proportional to the critical conditions and critical pressure, and every gas have different critical temperature and pressure, which makes this parameter different for different components. Similarly, the b parameter that is used in these equations is also represented by equation which is shown up here, and b is also proportional to some constant and some critical temperature and pressure. So every gas have different critical temperature and pressure, makes this parameter different. So once you calculate a and b, then you can use this equation, which shows that the compressibility is not linear, it's not even squared, so that the compressibility is basically a polynomial. So what they did, basically they introduced a compressibility equation like this one, and this equation is basically coming from here, from your main equation. Okay, I'm not going into a derivation, but I'm just telling you, like, this compressibility equation is basically another form of this equation, which is the main equation of P-Robinson equation of state, and they're represented like this form, which have some capital B's and capital A's. Now they need to find out what is capital B, capital A. So for capital A, they put this equation, which is used, which has alpha A, which is calculated from here, also the pressure divided by the gas constant and the temperature, which is at working temperature. Similarly, B is shown up here, which contains B, which is calculated from here, and also the pressure, the governing pressure, the constant, the gas constant, and the temperature. So once you calculate A and B, you can put them here. You can find out that this equation is a cubical equation. So the result of the cubical equation must be 3 different roots, right? So because they have 3 different roots, one of the root is your answer. Means one of your compressibility factor is your answer. I will explain this when we are doing MATLAB part. Now this is fine for the pure component, but what about mixture? If you have a mixture of gas, if you have 2 different gases, then you need to have a mixture of the gases. So how we can define the mixture? The mixture of the gas can be defined by this equation. Okay, so if you have 2 different or 3 or 4 or 5 components, you can see we can put them here and we can get the mixed values here, and that mixed values are used inside the equation. Okay, similarly you have the mixed value of the volume factor, which is B, right? So you can see here we have, this is for the pure component, but if you're using a mixture, you can use this component for a mixture. Okay, so you have multiple components A for different gases. You can mix them together by using this kind of a formula, which can mix them together to give you one particular mixed result for A, and similarly the mixed result for B. Okay, however, you can see here we have some information which is Kij. Kij is nothing but interaction between the molecules. You know that every molecule, for example, if you have a gas and you have a liquid and gas have different interaction. If you're talking about the same gases have no attraction, but dissimilar gases have interaction. Similarly, dissimilar phases also have interaction between the molecules. So this parameter, which is Kij, is also representing the interaction between the molecules. So how we can use this equation, particularly this equation, to find out the compressibility of a gas for a pure component or for a gas mixture. This is what we are going to do in the MATLAB. So let's open up the MATLAB, and these files I will share with you later on. First, I will open up a file that is saved here, compressibility for pure components, and I save this Ping-Robinson equation of state, which is the file for the pure components. So in this particular example, I'm taking the example of a carbon dioxide. So what information I need from the carbon dioxide? I need to have the information regarding what is the temperature, at what temperature you want to find out the compressibility, at what pressure you need to find out the compressibility. So at the temperature, the unit of the temperature that we are using in this particular example is Kelvin. At what pressure units are in Pascal. Similarly, the critical temperature information for that component, which is carbon dioxide, is represented in terms of Kelvin. Similarly, we need critical pressure in terms of Pascal for that gas, and also we need a centric factor for this gas, which is shown up here. Just want to show you this in terms of comment that this information is required here. Similarly, we need molecular weight, which is used basically to find out the density. And also this information, if you put liquid U is equal to 1, it means like they will calculate the fugacity of the liquid phase. Fugacity is basically a real pressure, okay? And normally when you talk about the pressure, the partial pressure of the gases, the partial pressure is not the real pressure, but if you calculate the gas fugacity, that is the real pressure, okay? And obviously for liquid phase, the fugacity or the real pressure is different. For the gases, the real pressure or fugacity is different. So if you put liquid O is equal to 0, then they will calculate the vapor fugacity instead of a liquid viscosity. Apart from that, they are also calculating the compressibility, and they are also calculating the liquid density. So the function that we have here is Z phi density. So this is the function. The function name is Ping-Robinson, and the input parameters are temperature, pressure, critical pressure, centric factor, molecular weight, and liquid O. If liquid O is equal to 1, it will calculate the liquid viscosity or liquid compressibility, or even the liquid density. If it is 0, then it will calculate the gas density, fugacity, and the compressibility. The gas constant is 8.314, which is the unit are joule per mole Kelvin. First, we need to find out the reduced temperatures, and the reduced temperatures and reduced pressures can be calculated by this formula, which you are already familiar. And the parameter for equation of state now we are going to calculate. And if you remember the equation, that is this equation, you can see here this part is basically calculated here separately, okay? Similarly, the alpha part, which is the combined part, which is this together part, is calculated here separately, okay? This m is this whole m. When you put them m here, you will get this equation, okay? Right. And the a and b, which is also mentioned here, this is the a and this is b, which we need to calculate. So we calculate a and b here, and the capital A and capital B, which is shown by this formula, is also calculated here. This is for capital A and this is for capital B. Now the idea is to calculate the compressibility. So this whole equation is put it here. Inside this, this is the function, the MATLAB function, which is used to find out the roots of the equation. So inside we put the equation, which is this particular equation, this is 1, this is supposed to be 1, this is supposed to be minus 1, so we can put it like this: 1 minus 1 by 1 dash b minus 1 dash b plus this is supposed to be a minus 2b minus 3b, a minus 3b minus square minus 2b. Similarly, all the z things we will put inside, okay? So based on this one, they will calculate the compressibility, and they will calculate 3 different roots. One of the root is your root, okay? First thing we need, that in this case the compressibility is given in terms of both real and complex numbers, okay? But we need only the real numbers, we don't need the complex numbers. So first we need to convert all those one in a real number. So this is the command which is used to convert all them into a real numbers. So as I told you before, if the liquid 2 is equal to 1, they will calculate the liquid liquid compressibility. If liquid 2 is equal to 1, they will calculate the liquid compressibility. If this one is 0, then they will calculate the gas viscosity. Once they calculate the gas and liquid compressibility, now you can use the viscosity formula. This is the formula which is also basically what you can say also derived from this equation, the main equation. Obviously the formula is not mentioned here, but you can also use that formula, and that formula is mentioned here. You can use the formula directly here, which is represented like this, and all the things that you already calculated before, which require the compressibility, the B, the capital B, the A, all of these terms we already calculated. The only thing you need to know is just put this formula correctly, and they will put the values here and they will calculate the viscosity for you. Okay, now once the viscosity is calculated, you can use this simple equation which I you remember that when this density is equal to pressure times molecular weight divided by Z multiplied by R multiplied by T. We already have the Z, we already have the molecular weight, we already have the pressure, we already have the gas constant and temperature. Using this, you will be able to find out the density. Okay, and the result that we can put them inside the brackets, all the results, the compressibility, the viscosity and the density inside the bracket, and this result will be shown up in your command window. So all you need to do is you need to pick up, now obviously this is a function, we cannot directly run the function, but we need to put the values of the function, then only we can run. The example is mentioned here in terms of a comment. So all you need to do is just copy this this part of the example, all of this codes, and write it here. Let me clear the screen, and you can type this whole function here. And let me again talk about this function. What this function is? This function is this is the function name. They will take in some information. What that information they will take in? The temperature, the pressure. The pressure is mentioned in terms of Pascal. Okay, so this is just a conversion of simple bar into Pascal. Then we need to know the critical temperature of the carbon dioxide. The critical temperature of the carbon dioxide is 304.21. Then we need to know what is the critical pressure of carbon dioxide. That will be in terms of Pascal is 7.382 times 1 is power 6. This is just a conversion of megapascal to Pascal. And similarly, we need to know the eccentric factor of carbon dioxide, which is 0.225. And we need to know what is the molecular weight of the carbon dioxide. That will be in terms of kg per mole. This is in kg per mole, okay, 0.044. And similarly, we need to put the value of liquid. Liquid is equal 1. If you put 1, it will calculate the liquid density, viscosity, and the compressibility. If you put this one 0, it will calculate the gas phase properties like density, viscosity, and compressibility. Let's enter. Now they are asking where the file is located. So first, let me change the location of the file. Now, if you can run this command, you can see here we can get the result. If you just make it up a little bit, you can see the first part in there. They will give us the result is the compressibility, which is 0.9855. The second is the viscosity, which is 0.9857, and the last one is 3.9854. The density units are different. Okay, so that's why you can have a different numbers here. So in this way, we can able to find out what is the compressibility, the viscosity, and the density. So let's jump on to another part, which is if you want to how you can find out the compressibility of a mixture. So let me clear the screen. So this is in this particular folder we have 1, 2, and 3 files. This is the file which is used for saving. Okay, 1, 2, 3 file, and the file that you need to open is the compressibility file. Okay. So in the compressibility file, how we'll start, I will just clear up the workspace and clear up the command window. Then I start by entering the critical temperature of both gases. So in this particular example, I'm finding the compressibility of methane and carbon dioxide. Two gases, they are combined together. Okay. So first we need to find out what is the critical temperature and pressure. Critical temperature I will put inside the bracket, the first critical temperature space, the second critical temperature, bracket close, put semicolon, so that you can have the critical temperature. If you put this whole thing on your command window and see what the results you will get, just put it here, paste and enter. You can see this TC basically contains two critical temperature. The first one is for methane and second one for carbon dioxide. Similarly, critical pressure for both components, both gases will be put inside the bracket and shown up here. And similarly, the eccentric factor for both gases will be shown up in this brackets. And the composition of this gas is like, for example, in this case methane is 98% and carbon dioxide is 2%. We put them inside the bracket, and the number of components that we have in this case is 2. You can have multiple components. If you want to put multiple components, 3 or 4 or 5, you can put them. And since I told you before, there is an interaction between the molecules, between the gases, and that interaction, if you open up this one, you can see this formula, the formula that is used for mixture. Inside this formula we are using this term 1 minus Kij. Kij is the binding interaction between the carbon dioxide and methane. So we have the parameters. So in this particular example I take these parameters from Aspen HYSYS. So the parameters are like this: 0, 0.1, space 0.1, comma, semicolon to put to the next line, 0 and 0.1. Okay, I think you can put it like this instead of like this. Yeah, now better. So this is how you can write the binding interaction parameters, which should be in IJ form. Okay, so it should be like because there are two components, so we have 2 by 2 matrix. So 2 by 2 matrix will be 0, 0.1, and the next line 0.1 and 0. Okay, so here we just give the information for the critical conditions, critical temperature, and the interaction parameters. Now we use a function called fig_compress. I already opened this one here. So let me go inside to the compress fig.compress and show you what is happening. So again the same thing is happening like in case of a pure component, but this time we have a mixture. Instead of only one reduced temperature and reduced pressure, we have a multiple, because we have two components, so we have two reduced temperature and pressure. So this will give us two reduced temperature and reduced pressures. Similarly, the alpha value that I talked about before in the theory, this is the alpha value. This value also requires two because we have two different gases and two which have different eccentric factors and different reduced temperatures. So this value also required to be having for different components. So what we are doing basically, we create a function, another function for alpha function. This inside this function I put this formula. This formula I need to put it inside this function. Okay, and what this function is doing basically, they will calculate the value of alpha for you. Okay, so instead of writing everything inside this this file, you need to make it separate function, so you don't have to be messing around in this particular file. Similarly, the A and B that we talk about in the theory, this one, now we have two components, so we need to calculate for two components. That's why we are putting them inside the for loop command. Okay, because we need to calculate these two values for each of them. Similarly, we need to use the mixing rule because we have two different components, and in the theory we talk about this part, right, which is basically used for mixture, and all we did in this particular example is just put them here. So Aij is shown up by this this equation, and Bij is this equation. So slight modification in this equation, I also add a binding interaction parameter here, which is shown up here. You can remove this one also if you don't want. You can remove this one. Okay, no need if you don't want this. So let me, if you remove it, it's up to you. Okay, so after this, so we calculate Aij and Bij, which is basically this one, this information. Then we need to calculate these whole terms, which can be calculated by using this formula. Okay, after this we'll get one values here, one values here. Then we can able to calculate the capital A and capital B, which is for the mixture, not for the pure components, by using this formula. The only thing you can see here, this AM and BM is for the mixture. That's why we have this whole part, and this whole part is for the mixture, not for the pure components. Then again we go to the same formula that I talk about in the pure components basis, this formula, which is basically used to calculate the compressibility. Not in this time we are calculating the compressibility for two components. So again the same thing is happening. We need to convert this z into real because we got results both in real and complex numbers. So we need only real numbers, so we just take out the real numbers from here, and this part is used to find out if you are going to find out the compressibility for the liquid or gases. For example, if you look at the this function input, I put this phase. If you put phase is equal to liquid, Lig, it means it will calculate the compressibility for the liquid. If you put phase equal to gas, it will calculate the compressibility for the gas. So how you put? You need to put this one either liquid or gas, okay, depending on this information, which I will talk about just a little bit after explaining this one. So after you finish compressibility, again we need to find out the fugacity, but this time we need to find out the fugacity for the mixture. So this whole information is basically used to find out the fugacity for the mixture. So if you go to the compressibility file, which is the main file, you can see here I put this function here, which is this function, and I am adding the temperature, the pressure, the critical temperature, the critical pressure, which already been added before, the centric factor, the composition, the number of components, the binary interaction parameter, and the phase that I'm going to find out. So in this case, if you enter, you will get both fugacity and the compressibility for a gas phase. So if you enter this one, you can get the result in a command window. So the first result will give you two different information for pressures because we have different gases. So we will get the first number is for the fugacity of the methane, and the second number is the fugacity of carbon dioxide. And since both components will give us only one compressibility because we have mixed component, so the compressibility of the gas is 0.9140, which is under these conditions, okay, for the methane and carbon dioxide gas. So I hope you understand this information regarding how to find out the compressibility for the pure component and the gas. If you have any